Hello and welcome. I'm going to talk about a new algorithm for the vertex-weighted global minimum cut problem. This is joint work with Julia Chuzhoy. Uh, in the most classic version of the problem, we're given a graph, an undirected graph, and we need to find a minimum set of edges whose removal disconnects the graph. Karger and Stein solved this problem in the 90s. We are using random edge contractions. This is a classic algorithm textbook. Later, Karger in 96 designed an algorithm for the problem running in near linear time using sparsifiers and k-respecting trees. Now, for the vertex cut version, we're given a graph, and we need to find a minimum set of vertices whose removal disconnects the graph. Hensinger, Rao, and Gabo showed that this problem can be solved in M and time via a push relabel method. And this has been the state of the art ever since for this problem. Let me mention that there's been a lot of effort recently on different variants of the global minimum cut problem, whether it's directed or vertex capacities, deterministic, etc. Many exciting results. Now, the main result in this paper is a new algorithm that breaks this 30 years old barrier. This new algorithm runs in time mn to the 0.99. This improvement might not seem like a lot, but conceptually it is a very interesting progress. So our algorithm can be described by three algorithms. Each one specializes in different settings. So the first algorithm is for the case where S, which is the separator in the global minimum cut, is small. So let's say we have a global minimum cut that has the separator S, and then there are the part L and then the part R. So if you remove S, then L and R are going to be disconnected. Now, for the case where S is small, we follow a method that was used in the unweighted case. We subset on a subset of vertices so that with sufficiently high probability, there is one vertex, one terminal that was chosen in L, and 0 terminals in S in the separator. And then we can use the isolating cuts lemma in order to compute for each terminal V a minimum cut between V and the rest of the terminals. Now, since no terminal was chosen from S, one of those isolating cuts will be the global minimum cut, and we'll be able to answer correctly after n to the 1 minus epsilon repetitions. Okay. The second algorithm specializes in the case where S might be big, but the graph is not too dense. So as you can see, M is smaller than n to the 2 minus 2 epsilon. In this case, we're going to define the set of terminals as all of the vertices whose degrees are more than n to the 1 minus epsilon. Now, this immediately implies that the size of T, the number of terminals, is at most 2 times n to the 1 minus epsilon. And the main observation that we have here is that at least one vertex in T, one terminal, must lie in L. So since we know that every vertex in the separator is connected to some vertex of L, and this is true because if it wasn't the case, then we would be able to move that vertex from S to R, reducing the size or the weight of the global minimum cut. So we know that every vertex in the separator is connected to L. And so the total number of edges incident to L is at least S, at least as the number of vertices in the separator. Now, since the separator is at least of size n to the 1 minus epsilon times L, we know that at least one vertex in L must have degree that is at least n to the 1 minus epsilon, and so it must be in T. We must have included it in the set of terminals in this case. Now, since X is in L, then we know that the total weight of the nodes in the separator without the neighborhood of X is at most the weight of L, which is at most the weight of R. Now, the assumption here that the weight of L is smaller than the weight of R, this is just without loss of generality, and the assumption that the statement that the weight of S minus the neighborhood of X is smaller than the weight of L. This is simply because those nodes in S without the neighborhood of X in the maximum flow from X to any node in R, there are flow paths that go through L and to those nodes, and so they cannot be of weight bigger than the weight of L. So what we do is we just sample Yx, sample a node uniformly at random by weight from the set of nodes without the neighborhood of X. And then we know that if X belonged to L, then Yx belonged to R with constant probability. And then we just compute a minimum cut between X and that node Yx for each X in T, for each one of those terminals that we chose. Now, given those two algorithms that I just described, algorithm 1 and algorithm 2, it is easy to see that we immediately have an algorithm that runs in time m to the 1.5 for the problem, for the global minimum cut problem. Now, the third algorithm, which is the most involved one, focuses on the case where the graph might be dense. So as you can see, m is bigger than n to the 2 minus 2 epsilon. And also, we're left with the case where L is smaller than n to the 1 minus epsilon times S, which is smaller than n to the epsilon. So L is also quite small. There aren't many vertices there. Now let me recap the algorithm for unweighted graphs from LNP 21. So first, just really in a high level, right? So first, we select a set of terminals where we add each vertex with probability 1 over L, the cardinality of L. Now we know that with high probability, T is a good set of terminals, which means that there is exactly one vertex that is a terminal that was chosen from L. And if we call this vertex X, then we know that S without the neighborhood of X does not have terminals. There are no terminals that were chosen from that subset. So this just means that this is a good set of terminals. And also, with high probability, we know that the total number of terminals is smaller than n over L. Right, this is straightforward. Now, for each terminal U, we compute maximum flow between U and the set of terminals without the neighborhood of U. Right, and we do that in a sparsified graph GU that was constructed using sparse recovery sketches in a clever way. Now with high probability, each one of those sparsified graphs GU contains at most L times the optimum number of edges. Optimum is the number of edges in the global minimum cut. And so the total running time is n over L times optimum times L, which is just n times opt. Now, since the minimum degree is of every node is at least the optimum, then the total time is just near linear. Now, what we do is we follow a similar scheme to that one. We pick a subset of terminals T. In our case, the sampling is adapted to weights, so that with high probability T is a good set of terminals, which again means that there is one terminal in L, that the set of nodes in S in the separator without the neighborhood of X, we did not choose any terminal from that subset. And so there is one terminal like that, right? This is the requirement. And also for each one of the terminals, for each X, we compute the maximum flow between X and T without the neighborhood of X. And then we just return the smallest one. However, the specification arguments from the unweighted case do not follow immediately. And that is for several reasons, mainly because the optimum may be much higher than n in our case, in the weighted case. And so the minimum degree arguments does not hold anymore. And another reason is that in order for T to be a good set of terminals, the sampling in our case is weight proportional, not degree proportional, like in the unweighted case. This makes other parts of the analysis to stop working. Okay, so now let me focus on exactly how we make sure that the graph the graphs are sparse. So given a graph G, we use its split graph, G prime. Now this is a classic transformation from a vertex-weighted to directed edge capacitated graphs. In this transformation, we have in copies and out copies for every one of the nodes. And also the set of edges. For the set of edges, we have two types. We have special edges. So for every node in the given graph, we have for every node V, we have a special edge, V in directed to V out, of capacity the same as that node. And we also have the second type of regular edges. So for every edge between U and V in the given graph, we have the edges, one from U out to V in and one from V out to U in. And the capacity of those edges is very high. Now this is an illustration, right? We have the graph G on the left, which is just a path of length 2 with weights 1, 10, and 1. And then on the right, you can see its split graph, right? The red edges are the special edges, and then the blue ones are the regular edges. Now, one might think to use that transformation as directly as a reduction to global minimum cut in directed graphs with edge capacities. Unfortunately, this does not work as is because there could be cuts in the split graph that do not correspond to any vertex cuts in the original graph. For example, you can see here, if we consider the cut in the split graph that has z out on one side and the rest of the nodes on the other side, this cut is the minimum cut, but it does not correspond to any vertex cut. Now, the general framework that we have, in the general framework, we start with G, we construct a split graph, and then we send it to a pre-processing step. This gives us F1 with certain requirements that we can run on the faces, right? We run the first, second, etc. The total number of faces is going to be just a polylog of the maximum weight, so it's not too much. And then eventually we return the global minimum cut. Now in the pre-processing step, we compute the maximum flow in the graph with only heavy nodes. Okay. Now the first claim is that there is an optimal flow that does not use edges entering to the neighborhood of S from nodes other than of S. This again generalizes an argument from LNP. Now, why this is correct? Assume that there is such a path, as you can see below, because the edges that go from S to the neighborhood of S have high capacity, infinite capacity essentially, we can just ignore that curve and instead add capacity on that edge. And so we can just assume that there are no such edges. Now the second claim is that the number of heavy nodes in S without the neighborhood of S is small. It's at most the weight of L without W. This is similar to an argument I described before. Now, the reason for that is that if we consider the maximum flow from S in L to a node in R, and then we consider the flow path decomposition, then every path from S that go through those nodes in S without the neighborhood of, in capital S in the separator without the neighborhood of S, must go through a node in L, and so it couldn't be that their weight would be bigger than the weight of L. And so that's about the weight. Now their number is at most the weight of L divided by W, which is just minimum bound on their the weight of each node. Now what follows from those two claims is that if we have a node V with degree that is bigger than the weight of L divided by W, then we know that V cannot belong to L. It must belong to either the separator or to R. And so it is possible for us to add a shortcut edge from its out copy directly to T and ignore all of the other edges that go from it, right? So since we know that V must belong to S or to R, it is possible to add an edge from its out copy directly to T without changing the value of the global minimum cut. Okay? So this is a very important concept of shortcutting. We add a lot of shortcuts in a way that will not increase the value of the global minimum cut if we're focused on the right terminal. Okay, now as far as the faces. claim 2 does not work here because the number of nodes in the separator without the neighborhood of S may now be the weight of L divided by W prime. For W prime, that could be much smaller than W. And so there could be many nodes. And so we need another way to sparsify the graph. All right, so let me just add that in this phase, in phase I, we focus on the nodes Ui, which are the set of nodes in the graph whose weight is bigger than Mi, and then Mi is getting smaller and smaller in each phase. Okay, so one of the main technical contributions in this paper is the following. So what we do in phase I is we find a partition Q and Q prime of Ui, the sort of relevant nodes in the current phase, such that the following two requirements hold. The first one is that Q prime doesn't have a big intersection with the separator. So the intersection of Q prime and the separator is just, it's at most n to the 1 minus 4 epsilon. And the second requirement is that if Q is bigger than that number, then we want to be able to compute a cut X star Y star in H in the residual network such that the residual capacity of the edges in the cut, so from X star to Y star, is close to the value of the maximum flow in the residual network from S to T. T is simply a node in R that is connected to the terminals that are not the neighborhood of S. Now, if a node U has a lot, if the number of edges between a node U and Q prime is bigger than 2 times n to the 1 minus 4 epsilon, then similar to before, we know that U does not belong to L. And so again, it is possible to add a shortcut edge from U out, from its out copy, directly to T. All right, and ignore other outgoing edges from U out. All right, that allows us to sparsify the graph. And another thing that allows us to sparsify the graph is the following. So for Q that is, again, bigger than n to the 1 minus 4 epsilon, if we think of E prime as the edges going back from Y star to X star, then in any maximum flow in the residual network H, those edges do not contribute much to that maximum flow. And the reason is that for every one such edge that goes back from Y star to X star, there are 2 edges in the other direction from X star to Y star. So we can just remove all of those edges that go in the direction between from Y star to X star without changing much the value of the global cut. Okay, so these two will allow us to sparsify the graph significantly. Okay, now we want to be able to find such a partition Q prime, and how are we going to do it? So for simplicity, it might be easier to think of just 2 weights, maybe 1 and M. M could be high around N. So let's think of a graph J that is a subgraph of the residual network H that contains only nodes reachable from S through heavy edges alone and not anything else. Okay, and so considering such a graph J, we're going to go through regular edges that have high capacity and also special edges of weight M, and also nodes Vn for light edges. So for example, those blue edges in R, we are going to get where we might be able to get there to their in copies. Okay, so this is the graph J. And now we define Q to be the set of relevant nodes, so the set of nodes that are currently relevant in UI, U in UI, so that their in copy belongs to J and their out copy does not belong to J, right? So this is the set of nodes Q in the beginning. And the set of and Q prime is simply the rest of the relevant nodes, UI without Q. Now we will have a few iterations that will change where some nodes belong to. And yeah, so if there is a set of edges B, this is a crucial observation. If there is a set of edges B that those edges are far from being saturated in a max flow FH, the residual network from S to T, then most of those edges, most of this batch is not in S, right? Because we know that in S they would be saturated. So we know that they're not in S, and so what we do is we repeatedly find such bad batches of edges B, and then move them from Q to Q prime. And the way that we do it is using minimum cost flow. Now let me show you how this works. So so first we consider all of the nodes that are outside of J, and we merge them into one node, which we call T prime. And this is just for the sake of finding Q and Q prime, finding this partition. So so this is how we define H tilde. Now we find bad batches B, then we move them to Q prime using min cost flow. How are we going to do it? Okay, so we define the cost of all of those edges, all of those blue edges, those edges that their in copy is in J and their out copy is not in J, so edges that correspond to Q, as the cost is going to be 1, okay? And the cost of the rest of the edges is going to be 0, right? So that's an incentive not to use those edges in general. Okay, so let's say in the first step, we run a minimum cost flow on this graph, and we get that the edges E4 are not used, right? And so what we do is we take those edges, we take the nodes corresponding to those edges, and then we remove them. We remove those nodes from Q, and we add them to Q prime, right? Then in the next iteration, the cost of E4 will be 0. The cost of the rest of the blue edges will still be 1. All right, and now again, run the minimum cost flow, and remember that now the algorithm will try to avoid to use those remaining blue edges. So let's say it succeeded in not using the edges of E3, and so we remove E3 from Q, the corresponding nodes from there, and then we add them to Q star. And then in the next iteration, the cost of E3 and of E4 is going to be 0, but the rest are going to still be 1, etc. We can continue. Then we'll again we remove E2 now from Q and add it to add those nodes to Q prime. And then in the next iteration, the cost of all of those E2, E3, and E4 will be 0. So the algorithm would like to use them. That's an incentive to use them. And then E1 is the only set of edges that currently is going to be 1. But at the end of the day, no large batches can be found. So at this point, the E1 the algorithm cannot avoid using it, and so generally no large bad batches can be found at the end. And so in this case, most spatial edges, V in to V out, where V is in Q, are close to being saturated in a maximum flow FH, right? Because we remove all of those edges that might not be used from Q, and so we are only left with those that are close to being saturated. And that gives us a way to compute the corresponding cut, the X star, Y star. Right, so this is how we get the partition Q star, Q prime. Now, how are we going to construct J so that the graph is sparse enough? So in order for the constructed graphs to be small, well, we have that J satisfies the following two requirements. The first one is that it doesn't have a lot of out copies, okay? And the second one is that for every vertex that is outside of J, the edges entering it from J are going to be a few, and their total residual capacity is small, okay? And now these requirements allows us to sparsify the graphs. Now, J might be too large, so let me just say that we do not compute it directly, but we iteratively either add shortcut edges and then augment the current flow by a significant amount each time, or the subgraph J is just small and with the desired properties that I mentioned, and so we just output it and turn at the algorithm. All right, so how are we going to get a graph J with those requirements? That again, we want a small amount of out copies and not a lot of edges or capacity outside of J, going from J outside of it. Okay, so a method that comes to mind is the local flow method. Now, let me recap what it means. It has been applied on unweighted graphs, and the way that it is working is as follows. We grow a small DFS tree from S, and then we pick a random out copy, U out, and then we simply augment in H the path from S to U that is inspired from the tree. So there is a path, and then we would, in our case, add a shortcut edge from U out to T. Now, can we do it directly here? Not really in weighted graphs. And the reason is that an out copy may have many incoming edges, as opposed to unweighted graphs where it is not the case. Here, it can have many incoming edges. And so the DFS tree would be large. It could be that the DFS tree is just large and mostly in copies, and so we cannot shortcut in copies to T. We can only do it for out copies. And so what do we do? So we would have to grow a large DFS tree or subgraph in order to be able to pick out copies, in order for us to discover a sufficient amount of out copies to sample from for the local flow method to work. But since we now discover a large subgraph or DFS tree, in order to bound the total running time, we make sure that the number of iteration is small. And the way to do it is by only considering heavy edges. However, this leaves us with an issue that about the second requirement, that an outcopy without VJ could still have many edges from VJ, many edges, and we need to be able to handle it. The way that we do it is by extended local flow. Instead of just shipping paths, we consider flows that might not be path, might be just a flow, and that this way we're able to cover for this issue, to overcome it, and then shortcut into T, and have the graph J with the requirements. Now, finally, I want to mention where the subgraph oracle. So during the run of our algorithm, we may need to quickly output a subset YL that has a few neighbors in a given subset Z. And we also need to output the corresponding edges between them. Now, just to output such a subset might be easy via sampling. To output those edges seems more challenging, and the way that we solve this problem is in a bulk. We make a reduction to triangle listing, and by this reduction we manage to process for each phase several terminals at once in a time that is smaller than n cubed, and you can see it here. You have in the bottom you have the terminals. So for the terminal TI, terminal TI is connected to BV if V belongs to YL. And then again, the terminal TI is connected to AU if U belongs to ZI, and there is an edge between AU and BV if the edge exists in the graph. Now, each such triangle corresponds to an edge in that instance, and so since we know that the total number of edges should be small, just listing the triangles can give us the corresponding edges. Yeah, that would be all. This is my time. Thank you very much for listening.